We have been considering the solutions of quadratic equations, equations of the form ax squared plus bx plus c is equal to 0, where a, b and c are constants. And we derived this equation, the quadratic equation, to give us the solutions to equations of this form. The quadratic equation is negative b plus or minus the square root of b squared, subtract 4ac, divided by 2a. And of all of the pieces here which are important, it is a bit under the square root, b squared subtract 4ac, which is the really important part. Because we saw with some examples last time that if b squared subtract 4ac is positive, then we will be able to square root it, and we'll therefore have two solutions, one where we add that square root and one where we subtract it. If b squared subtract 4ac is 0, then we'll only have one solution. Whether you add or subtract 0, we'll get the same answer. If b squared subtract 4ac is negative, we have a problem. We cannot square root it, and there will be no solutions. So this thing, b squared subtract 4ac, is very important. We give it the name the discriminant. Let's formalize all those results we've just talked about. So the discriminant of the quadratic equation ax squared plus bx plus c equals 0 is given this symbol capital delta, and it's defined to be b squared subtract 4ac. If the discriminant is greater than 0, then the quadratic equation has two distinct real solutions. If the discriminant is 0, then the quadratic equation has one real solution. Sometimes we call that a repeated solution. If the discriminant is less than 0, then the quadratic equation has no real solutions. If you are aware of why we are specifically saying real solutions here, then you will understand its significance. If it just looks a bit odd to you, then you can completely ignore it and just think of this as talking about whether we have two, one, or no solutions. There is one other case it's very useful to know about. If the discriminant is a square number, then the quadratic equation can be factorised using integers. If we can factorise quadratics, that's usually the quickest and easiest way to solve quadratic equations, but sometimes it's not so obvious what the factorised solution is. You may be struggling to do some factorisation. You can quickly check the discriminant to see if you get a square number, to see if it is even worth trying to factorise your quadratic. So let us make use of the discriminant to solve this question. Find the number of real solutions of each of these equations. So in part A, we have 6x squared is 9x subtract 1. However, we can't use that form to work out the discriminant. We must have it in the ax squared plus bx plus c form to be able to use it. So I've rearranged that so everything is on one side with an equals 0 on the other. That means that the discriminant is b squared, negative 9, squared, subtract 4, times a, which is 6, times c, which is 1. The discriminant is 81, subtract 24, which is 57. The actual value is not so important to us here as the fact that that is greater than 0. Therefore, the original equation has two real solutions. In part B, again, we need to rearrange before we can get started. We can write this as 9x squared subtract x plus 6 is 0, and now we can use the discriminant. The discriminant in this case is negative 1 squared subtract 4 times 9 times 6. That is 1 subtract 216, which is negative 215. Again, the value is not so important to us as the fact that this is less than 0, and therefore we have no real solutions. And in part C, again, we'll need to rearrange. Let's write that as x squared plus 6x plus 9 is 0. In this case, the discriminant is b, which is 6, squared, subtract 4 times 1 times 9, which is 36, subtract 36, which is 0. So therefore that quadratic equation has one real solution. Or we may sometimes say it has a repeated solution. Can the quadratic expression x squared subtract 2x subtract 35 be factorised? Although this is not actually part of a full equation, we can still use the same ideas. The discriminant in this case is b squared, negative 2 squared, subtract 4 times a, which is 1, times c, which is negative 35. Okay, negative 2 squared is 4. 4 times 1 is 4, times 35, or 2 35s are 70, so 4 of them are 140, and the negative make it positive. So we're adding 140, so the answer is 144, and 144 is a square number, it's 12 squared, so therefore the answer is yes, we can factorise it. This is actually not the most difficult one of all to factorise. Because the number on the end is 35, it can either factorise as 1 and 35 or 7 and 5, and it doesn't take very much to see that this is x minus 7, x plus 5. But we weren't actually being asked to find the factorisation, just to prove that it was possible. Find the value of k for which the equation x squared plus 5x plus k equals 0 has a repeated real solution. So k is a constant which we have to find, and if this quadratic equation has a repeated real solution, then that means that its discriminant is 0. If its discriminant is 0, that means that b squared, b is 5, subtract 4 times a, which is 1, times c, the constant, which in this case is the k we do not know, then that is 0. So 5 squared is 25, subtract 4k is 0. That means that 4k is 25. And if our original quadratic equation has a repeated solution, then the value of k must be 25 over 4. Find the set of values of k for which the equation kx squared plus 3x subtract 1 equals 0 has two distinct real solutions. If we have two distinct real solutions, that means that the discriminant is greater than 0. The discriminant in this case is 3 squared, subtract 4 times k times negative 1. That is what we need to be greater than 0. So we have that 9 plus 4k is greater than 0. That means that 4k is greater than negative 9, and therefore k itself must be greater than negative 9 over 4. For any value of k greater than negative 9 over 4, our original quadratic will have two distinct solutions. For other values of k, it won't. Find the set of values of k for which the equation 2x squared plus kx plus 1 equals 0 has no real solutions. If the quadratic has no real solutions, then its discriminant is less than 0. In this case, that discriminant is k squared, subtract 4 times 2 times 1. So that is what has to be less than 0. In other words, k squared subtract 8 is less than 0. So k squared is less than 8, and therefore k itself must be less than the square root of 8 or greater than the negative of the square root of 8. These are the values of k for which the original quadratic equation has no real solutions.